Okay, let's get started. We do have kind of a long lesson today. We're going over 4.1, 2, and 3. We kind of do all of it. So it's going to be a long lesson. But anything you don't get, remember I am recording it. I'm not sure why it's not recording. Okay. I'm not sure why it's not displaying. All right. See if this works now. There we go. All right. So we got it working. Like I said, it's gonna be kind of a long class. We're starting a little late. But we're going over 4.1, 2, and 3. I'll pass back the test at the end of class if you want it. If not, I'm just going to dump it. I don't want to hold on to it. And if you don't want it, I don't need it. All right. So these are the concepts we're going to be going over. We're going to identify one-to-one functions, determine whether two functions are inverses, and find the inverse of a function. So honestly, 1 and 3, concepts 1 and 3, we've actually done before. Concept 2, we've kind of done before, kind of haven't. Uh, but all this stuff really shouldn't be that new to you if you've been keeping up with the course. So first, let's identify a one-to-one function. This is the definition of a one-to-one function. A function f is one-to-one if for a and b in the domain of f, if a does not equal b, then f of a does not equal f of b, or equivalently, if f of a equals f of b, then a equals b. Essentially, the only time something is one-to-one is 1x goes to 1y. Okay? What it really means that passes something called the horizontal line test. Y'all remember the vertical line test we had before? Determine if it's a function. What is the opposite of it? It just means does it pass the horizontal line test? If it passes the horizontal line test, it's one to one. So that means you have no x's and no y's repeated. If you have x's repeat, it's not a function. If y's repeat, it's not a one to one function. So in this case, basically, no y's repeat. We're okay here? Anyone still typing down or writing down? Okay. Ready to keep going? All right. So Yeah, so the horizontal line test is what we have here. So a function defined by y equals f of x is one-to-one function if no horizontal line intersects the graph in more than one point. That's saying the same thing I said before. No y's repeat. A function is one-to-one if the y's do not repeat. That's essentially what the horizontal line test is testing. Then no y's are repeating. Ready to keep going? Okay. So here's some examples. The first one, determine if whether the function is one-to-one. So essentially what we need to do is check are the y's repeating or not. So I have a 1, a 2, a 3, and then a 1 again. So because the ones are repeating, it is not 1-to-1. If the y's repeat, you are not 1-to-1. So in this case, because you have a 1 at 2-1 and a 1 at negative 2-1, the y's repeated, you have the same y happening in two different places. It is not a function. All right. Here's another example. Determine if the relation y, if the relation defines y as a one-to-one function. I'm not really sure what this stuff means, but one-to-one essentially just means the y's don't repeat. You don't have the arrow going to the same thing twice. All right. So because each of these arrows are going to one thing each time here, it's going to be, it is one-to-one. Heroes and villains. I can tell with Batman and Wolverine, but I know nothing about Green Lantern. Yeah, so it is one-to-one because each hero goes to one villain. You don't have two heroes going to one villain. Sorry? He's I know yeah, I think I know Juggernaut. He's isn't he like the really buff dude, right? With the helmet. And Bane's the guy with like the CPAP thing going on happening. Yeah, okay. I never watched the movie, that's kind of know the names. So now we're gonna use the horizontal line test here to determine if it is one-to-one. So what you're gonna do for the horizontal line test, you can draw a horizontal line and just kind of test, well, are you going through more than one point at any given time? In this case, you're not. Every single time, if this line was straight, you'd realize that, well, I only pass one line or one point every single time with a horizontal line. So it is one-to-one. So essentially, you just draw a straight line, a horizontal line. In this case, I have a computer, I can do this. If not, you can use like your pencil or a piece of paper or whatever. And if you go through every single point or go through the whole graph with a horizontal line or a horizontal edge and it only hits one point every single time, it means it passes the horizontal line test. In this case, it does, right? And there's no time where I cross 2 points at once with this horizontal line. You can use your pencil or another piece of paper, so it passes the horizontal line test. Ready to keep going? All right. Now in this case, I can use that same horizontal line or not to see if it passes this one. So in this case, well, it's pretty clear to see that you're not going to pass the horizontal line test. I'm hitting more than one thing at pretty much everywhere. So we do not pass the horizontal line test. It's not one-to-one. They are way too. All right. Now we'll actually deal with some math, with some numbers. I know this is when y'all love it, but let's go through it. So use the definition of one-to-one function to determine whether the function is one-to-one. So I have 3x plus 2, so that f of a equals f of b, then a equals b. So what you can do here is plug in f of a and see what you get. So f of a equals 3 times a plus 2. Or even here, even a better, or yeah, leave it f of a. So f of a equals 3a plus 2. And that's really all you can do. 3a plus 2. F of b equals 3b plus 2. Or 3b plus 2. So f of b is just 3b plus 2. F of a is 3a plus 2. Well, when will 3a plus 2 equal 3b plus 2? When a equals b. The only time these are true is when a and b are the same thing. So you can say 3a plus 2 equals 3b plus 2 only when a equals b. That's it. That's the only time. So 3a plus 2 equals 3b plus 2 only when a equals 2. When a equals b. And I guess you could actually solve this out if you wanted to. You could solve this out and say, oh, well, let's solve for a or b. So if you subtract 2 on both sides, these cancel, and you have 3a equals 3b. If you divide them both by 3, you get a equals b. So I guess you could just solve it all the way out to actually see it mathematically that, oh, f of a equals f of b only when a equals b. So if you have f of a equals f of b. Does that make sense what I'm saying, guys?
Yes.
So essentially solve f of a, solve f of b, set them equal to each other, and see what a and b, how they relate. Ready to keep going? All right. Now we're going to do the same thing with 3x squared. So do the same thing. Well, f of a will be 3 parentheses a squared, or just 3a squared. F of b will be 3 parentheses b squared, or f of b is 3b squared. So now we have f of a, whoops, equals f of b. We want to set these equal to each other and see, well, how does a and b relate? Well, we have 3a squared equals 3b squared. And just solve for a or b, doesn't actually matter which one, just solve for one of them, see what you get. If I divide both sides by 3, you have a squared equals b squared. And if you take a square root of both sides, what you get is that a equals plus or minus b. Or if you want to flip it, say b equals plus or minus a, it doesn't actually matter. But what you see here is that, well, a equals b and a equals negative b. Does that make sense what I'm doing, guys? Is it the plus or minus part that you got lost? Yes. And it doesn't actually matter where you put the plus or minus, the left side or the right side doesn't actually matter. So I just put on the right side just to put on the right side, but if you wanted to put it to the left side, it doesn't matter. Okay? Oh, I divided. So you have 3a squared equals 3b squared. So I want to solve for a here. That's what I'm doing. You can solve for b, it doesn't matter. So I divided by 3 because I want to get the a's by themselves. Or I want to get the a and the b by themselves. Make sense? So you have a squared equals b squared, and if you square root both sides, you get a equals plus or minus b. Well, that means a equals b or a equals negative b. That is not a equals b. Right? It can only be this. Because you have an a equals b and an a equals negative b, it's not 1-to-1. Make sense? Cool. Ready to keep going, guys? Yes. No worries. Got it? All right.
Actually, can I see my test? I know that's got paper.
Sure.
Something about writing it down.
I have some blank ones. You can just steal paper from here. I'll look for yours as well. Oh, yeah. All right. Ready to keep going, guys? All right. Now determine whether two inverses are functions. So, inverse functions, let f be a one-to-one function, and g is the inverse of f if the following conditions are true. Essentially, all it's saying is that if you have f of x and g of x, I think it's a little confusing. But you can copy it if you want to, but essentially what it's saying is that if f of g of x equals x and also g of f of x equals x, if these both are true, then f of x and g of x are inverses. That's essentially what it's saying. If f of g of x equals x and g of f of x equals x, then f of x and g of x are inverses. They both need to be true, not one or the other. They both need to be true. Okay? And that's essentially what this whole thing right here is saying. That they both, that f of g of x and g of f of x both need to be x. Ready to keep going? We're also copying. So copying? Okay. Ready? Okay. So we're going to do a few examples. So we have f of x and g of x. I want to determine whether these are inverses or not. So this can be a little confusing and hard to track. So what I like to do to make it a little simpler is I like to kind of color code it and do everything step by step. All right, so we'll actually do green and red. Okay. So f of x is going to be green, g of x is going to be red. So I want f of g of x I want this to equal x. And I also want g of f of x to be x. Okay? So remember, anytime you have something like f of something, like f of 2, you plug that 2 in for x, right? For f. Right? So if you had something like f of 2, for instance, you'd plug this in as 3 times 2 plus 6, right? Y'all remember that? I'm pointing that out because with f of g of x, it's the same concept, just more complicated because you're plugging in a whole function. But it's the same thing. You're going to take f of x, which is 3x plus 6, but instead of x, you're replacing it with g of x plus 6. Right? Instead of 3x plus 6, it's now 3g of x plus 6. The same way f of 2 is now 3 of 2 plus 6. Everyone with me? All you do is replace the x with what's in this parentheses here. So in this case, is g of x, you replace the x with g of x. Right? The same way we had f of 2, you replace the x with 2. Now we're replacing the x with g of x. And we know what g of x is. It's 1/3 x minus 2. So I'm doing it step by step by saying, oh, replace x with g of x, and then plug in the actual function. I think it just makes it a little more straightforward to see what's happening. Everyone with me? So distribute the 3 in. So 3 times 1/3 is just x. 3 times negative 2 is negative 6. And we still have this plus 6 to bring down. And negative 6 plus 6 is x. And that's what I wanted. I wanted this to equal x, and that's what I got. Great. And now we can do the other side. Sorry? Sure.
This is very similar to the sections we did.
Yeah, remember the composite function we had in the last? It was like g circle x or whatever.
Yes.
You g of f of x, like something like this, right?
Yes.
It's the same exact thing, except now we're instead of doing it with a number like g of f of 3, we're doing g of f of x or of a function or whatever.
Okay.
So it's a little harder, but yes, we've done this before. Yes. All right, so g of x now, well, that's 1/3 x minus 2. So g of f of x, we're going to take the g of x function, 1/3, and replace the x with f of x now. Okay? So f of x, we know what that is, 3x plus 6. And just like before, we're going to expand it all out to see what we get. So 1/3 of 3x is just x. 1/3 of 6 is a positive 2. This negative 2 we bring down, minus 2 to just get x. Make sense, guys? Yes. And for inverse specifically, no. But we've done this with numbers already. I was in the last test, but they won't ever be numbers because inverses we just want to prove this and that's it. Everyone else, are we okay? All right, let's keep going. Um, yeah, we can do this. So same thing. F of x will be green. G of x is red. So you want f of g of x. I want this to equal x. And also g of f of x. I want this to also equal x. Okay? So same thing as before. F of x is x plus 1 over 5. So replace the x with g of x plus 1 over 5. Well, g of x is 5x plus 1, right? So we have 5x plus 1 plus 1 over 5. Or 5x plus 2 over 5. And I copied this down right. So we can't really simplify this anymore from here. And that's not x, right? Because it's not x, that means this doesn't work, which means we don't need to check the other side. If it doesn't work for one side, you don't need to check the other one because it needs to equal x for it to work. So these are not inverses. You don't need to check the other side if one side doesn't work because if they both need to work for them to be inverses. So if one doesn't work, who cares about the other side if it works or not? It's not going to be an inverse. Are you ready to keep going, guys? All right. Now, how to find an inverse. This is probably the easiest thing of inverses, how to find them. all you really do, you have the steps right here if you want to copy the official steps, but these first and last steps are pretty useless. All you really need to do is just change x and y and solve for y. That's it. So switch x and y, solve for y. Oops. And that's it. Sorry?
Uh,
Uh,
the other math class we do a 4.1.
Oh, you're doing stuff like this, right?
Yeah, he put down like interchange and replace X by Y, all that stuff.
Yeah, it's always switch x and y, solve for y. Ready? Keep going. Okay. So a one-to-one function is given, and we are going to write its inverse. So I'm going to write an equation for the inverse function. I don't care for the graph itself, to be honest. What I am going to do here, we have f of x equals 2 plus 1 half x. So remember, f of x is just a fancy way of saying y, essentially. So y equals 2 plus 1 half x. We're going to switch the x and y's. There's no real math here. We're just switching them. So x equals 2 plus 1 half y. And now I'm going to solve for y. So I'm going to subtract 2 on both sides to get the 1 half y by itself. So subtract 2, subtract 2. X minus 2 equals 1 half y. And then multiply both sides by 2, because I don't want a 1 half. If you multiply both sides by 2, what you get is 2x minus 4 equals y. And that's your inverse. I mean, you could write a little more official, say, well, f inverse of x equals 2x minus 4. I guess that's kind of like the proper way to write it. But it's just notation at that point. You're just changing y for f inverse of x. That's it. You're solving for y. The only thing that stays the same with solving for inverses is you flip the x and y's. And then from there, just solve for y however you can. Make sense what I'm saying? So you see here in this step, we switch the x and y's. We had y equals 2 plus 1 half x. The next step, x equals 2 plus 1 half y. That's the only step that stays the same. And then what I did from there is I solved for y. I want y by itself because y by itself gives you that inverse. You get what I'm saying? What's the confusing part? Oh, because I want to get, you see the 1 half? I don't want that there. To get rid of something being multiplied, you multiply by its reciprocal. So you have 1 half, you multiply by 2. If you have 1/5, you multiply by 5 over 1. If you have 2/3, you multiply by 3 over 2. You flip the number, and if you multiply them together, they cancel each other out. Make sense? Everyone else, are you okay? All right. So now we have another inverse. It's a little harder, but it's essentially the same thing anyway. So x squared plus 3 for x is greater than or equal to 0. That part is important. We'll get back to that in a bit. But we have y equals x squared plus 3. And now we're going to flip the x's and y's. So x equals y squared plus 3. And now I'm going to solve for y. So subtract the 3 over. X minus 3 equals y squared. And then square root both sides. So the square root of x minus 3 equals y. And technically, you should have a plus or minus here, right? Because you're taking a square root of a variable. But because we're saying x is greater than or equal to 0, all you do is leave the positive one. I don't think we'll ever get into situations where you have to do anything other than that. I think we're going to always keep it like that. So I wouldn't worry anything about that. Just keep it positive.
This one, we can't. Why?
I mean, honestly, you could put it in front of the y. The plus or minus, you can always move it to any side you want. It doesn't actually matter. It actually technically starts with the y, and then you move it over. But yeah, but I guess the easy way just always keep it on the part away from y. You want y by itself anyway. And that's your inverse. I guess make it f inverse if you want to. And that's it. Any questions so far? Are we good? It's f raised to the negative one. So it's not f negative one. Like it's not f minus one. It's f to the power of negative one x. Any other questions, guys? All right. Um. Yeah, we're not gonna do that. That gets a little complicated. All right. 4.2. Not too much to do here, which is great. We are going to graph exponential functions. All right. That is the only concept we're going to do. This is the definition of an exponential function. Um, Again, this is really complicated. Essentially, what it is f of x equals some number raised to the power of x. So, like 2 to the x is an exponential function, 3 to the x, 5 to the x, one third to the x. Anything raised to a power of x, that is an exponential function. And it's called exponential because the x is in the exponent. I guess that's the best way to say it. Are we good here? No question, or are you still copying? Okay. I don't think that's going to be enough. We still have a whole other section to go through. We saw 4.3. Are we good here, though, guys? Good. Okay. So let's go ahead and graph it. Honestly, graphing it isn't too bad because I wouldn't memorize. I think there is some tricks to this, know how to do it. I don't bother memorizing tricks because they only work for one specific function, and it's kind of a pain to memorize a bunch of things. Just plug in numbers. That's it. And when it comes to exponential functions, start with 0. So x to the 0. And do y'all know that 3 to the power of 0 or anything to the power of 0 is always 1, right? Anything other than 0 to the power of 0 is always 1. So 3 to the 0, well, that's just 1. When x is 1, you have 3 to the power of 1, which is just 3. If you have 2, 3 squared is 9. I'm not going any higher than this. This is going to get huge at this point. So we have 0 right, so they're going up by 2. So you have 0, 1. Then you have 1, 3. Then 2, 2, 4, 6, 8, 9. Like this. Okay? And what you get is that the graph's going to look like this. That's what an exponential function looks like. It's going to start shooting up very, very quickly because exponents get very big very, very quickly. And we're not going to continue, so let's do dot, dot, dot. And do y'all know how negative exponents work? So if I say 3 to the negative 1, do y'all know what that is? It's a fraction. So anytime you have a negative exponent, you flip the base itself. So 3 to the negative 1, well, that is 1/3. 3 to the negative 2, well, that's 1/3 squared. Or in this case, 1/9. So if you have a negative exponent, what you do is you flip the base and you raise the whole thing to that power. So I guess 3 to the negative 1 is really 1/3 to the first power, which is just 1/3. 3 to the negative 2 is 1/3 to the second power, or 1/9. Are y'all with me? Because there's a point I'm trying to get to here. And the point I'm trying to get to is that it doesn't matter how big the negative is when it comes to exponents, it will never equal 0. There's no value of x I can plug into 3 to the x to make it equal 0. Okay? Did y'all see that? Because no matter how big this negative number gets, negative 100, negative a million, negative a billion, it's just going to be 1/3 to that billionth or millionth or whatever power. That won't ever be 0. It'll be close to 0, but never equal 0. Are y'all fine with what I'm saying there, logic-wise? All right, so I'm saying that because of that, you have an asymptote of y equals 0. You have an asymptote there because you can never equal 0 because this can never be 0. Something raised to the x power can never be 0 because this negative exponent stuff that I'm talking about. So that means exponential functions have a asymptote. Everyone with me? Okay. Ready to keep going? All right. Now we have 2 to the power of negative x. So 2 to the power of negative x, like I said before, just start with 0. So 2 to the negative 0, that's just 2 to the 0, which is 1. And now just go up, go to power of 1. You have 2 to the power of negative 1, or 1/2 to the power of 1, which is 1/2. So 2 to the negative 1 is 1/2. That's kind of what we just talked about. Are y'all with me? Okay. And let's just keep going. So 2 to the negative 2, well, that's 1/2 squared, or 1/4. Do y'all see how this is getting smaller from 1 to 1/2 to 1/4? You're getting closer and closer to 0. So you start at 0, 1. Or it's not 0, 1. Right here. And the numbers are getting smaller and smaller. Okay? So, I'm sorry? It's going to go down. It kind of flips. Because I know it's not going to be a proper table, but I want to show you guys, well, what happens when x is negative 1. You have 2 to the negative 1, or 2 to the first power, which is 2. Y'all see what I'm doing? I'm plugging in. The table's not really in order right now. I'm kind of just going to show you what happens on the other side of 0. So when x is negative 1, you have 2 raised to the negative of negative 1, or 2 to the first power, which is 2. Y'all see that? Any questions about what I'm doing there? And let's try negative 2. 2 to the negative 2. Well, negative negative makes it positive, so it's 2 squared or 4. So when x is negative 1, you're at 2 right here. When you're at negative 2, you're at 4 right here. So what's happening is this graph actually got flipped compared to the last one. So it's going down instead of going up. And that's what a negative does. If you have a negative exponent, it flips the graph. It's the same thing. I don't care. Decimals, fractions are the same thing. And there's a reason for this. Okay? But are y'all with me with the logic right here about all the negative exponents we're plugging in? Are y'all okay with this? Yes? All right. Because remember we said anything to the power of negative, you just flip the base, right? So isn't 2 to the negative x the same thing as 1/2 to the x? Don't see it? All right. So remember up here we said 3 to the negative 1 is 1/3 to the first. 3 to the negative 2 is 1/3 to the second. So 2 to the negative x is 1/2 to the x. You get rid of the negative, you flip it, and you raise it to that power. Right? 3 to the negative 2, you flip it, got rid of the negative, raise it to that power. Okay? Everyone with me right now? Or any questions about anything? We're good? All right, because these are two different functions, and I think they're going to explain it now. Yeah. So here's the official textbook definition of this stuff, and I'm just going to tell you what they kind of mean in my own words. I'm letting you. So essentially, the base of the function, the base of the exponential function, it can either be what's it called? It can either be a number bigger than 1 or a number less than 1. It cannot be 1 or negative. That's just the rule. It can't be 1, negative, or 0. Okay? So if it's bigger than 1, it's something called a growth function. So if you have something like 2 to the x or 3 to the x or whatever you want to the x power, like the number, the base itself is bigger than 1, it's growing. You see here, it's 3 to the x, it's going up, it's growing. And if it's a decay function, let's say 1/2 x or 3 to the x, or not 3 to the x, but 1/3 to the x. So anything less than 1 that's still not negative. Like this right here, 2 to negative x is just 1/2 x, right? So 1/2, it's smaller than 1. That's why it's decaying, it's going down. So less than 1, it goes down. Greater than 1, it's going to go up. And they're called growth and decay functions. I wouldn't say that. I would all honestly with these growth functions or in these exponentials, sorry, I would never leave a negative in the exponent. If you ever see a negative in the exponent, flip the base and get rid of it. I didn't do this here yet, so I just want to show you what happens. But I would normally not do it this way. I would flip the base, make it 1/2 x, and then graph it. It just makes it easier to work with because it makes it easier to kind of see. And honestly, with these functions, if you graph 1 point, that's all you need. If you have 1 point, you're good to go. You don't need anything else than that. All you need is 1 because you know the shape, right? It's kind of like it kind of curved like that. So once you have 1 point, you kind of know where the rest of it's going to go. Just kind of graph it normally. What do you mean about the decay? It's a decay function if the base is less than 1, and yes, it goes down. So stuff like 1/2 x, 1/3 x, whatever you want, as long as the base is less than 1, it's going to be what's it called? It's going to be decay. Here, the domain is always all real numbers. All right, so the domain's always all real numbers. That's something else to know. Everyone with me? Any questions? All right. Now we have one that's a little more complicated. but not really. So, I mean, just do the same thing we did before. 3 to the x minus 2. Plug in any x value you want. In this case, I would actually start with 2. The reason why is because if you plug in 2 into the x, you have 2 minus 2, right? Or just 0. So you get 1 plus 4 or 5. I mean, I'm doing that because, I mean, I get it. I've been doing this for a while, so I know what to look for. If you guys decide to just plug in 0, you would still get a right answer. It doesn't actually matter. So you can just plug in 2 or 0, whatever you want. You will get a point on the graph. It doesn't matter. But in this case, we have 2, 5. Oh, 2, 4, 6, 8, 10. Right there. Everyone with me? Any questions about what I'm doing? Are you okay with this? Yes. Makes sense? All right. So you have 2, 5. And remember I told you guys this exponent can never equal 0, right? Because this can never equal 0, f of x can never equal 4, right? It'll always be f of x equals some number plus 4. The reason I'm saying that is because with exponential functions, this number is always the asymptote. So I'm trying to show you the logic of what's happening, but at the same time, just know that 4 is always the asymptote. Sorry? Horizontal, yes. Because y can never equal 4, because this middle term can never be 0. That's the logic behind it, but it's really just whatever number is kind of adding or subtracting here, that's your asymptote. That's why in the previous examples, you saw here, this is technically plus 0. We have an asymptote at 0. Up above here is also technically plus 0, right? That's why you have an asymptote at 0. So whatever you're adding to at the end, that is your asymptote of y. So y equals 4 is your asymptote here. Are we good with that? Any questions about that? No? Yes. Yes. Yeah, essentially, yeah. That's exactly it. So if you have x plus 2, put the opposite, negative 2, right? And all you need is 1 point, because is this a growth or decay function? The base, look at the base. Growth, right? The 3 is bigger than 1, so I know that, well, it's going to look something like this, right? That's it. You really only need 1 point. Once you have 1 point, the rest is fine. Yes, it was 3 to the negative x, whatever. Yeah, it'll be decay. Because then you have to take the negative out and flip it. Are we ready to keep going, guys? Any questions? Okay. That's it for 4.2. Now 4.3. We have a lot. 4.3 is kind of long, but a lot of it is really just rules. Well, I say only rules, but still kind of annoying. So now we're dealing with logs. Logs are just the opposite of exponent. They're inverses of each other. So we're going to learn how to convert between logs and exponentials. We're going to evaluate logarithmic expressions, apply basic properties of logs, graph logs, etc. This is 4.3. I will say this is probably, I think it's probably the hardest thing we have left for the year. Yeah. The next few things aren't that bad. Like this and next week will be logs as well. So we're spending a long time with logs. But after that, it shouldn't be that bad, the class. Ready to keep going? Okay. Good? Okay. So definition of a log function. Essentially, y equals log b of x. That's what a log is. And it's equivalent to by equals x. So how to go between an exponential and a log, the way I kind of think about it is that if you have y equals log b of x, like this, you can flip it to an exponent. The way I think about it is that the base of the log is the base of the exponent. And then because the x and y's flip because they are inverses of each other, they flip on different sides of the equal sign. So the base stays the same. Well, the b and the x were together, but now they're going to flip. And that's how you kind of go between the two. That's kind of what works in my head. The base of the log is the base of the exponent, and then you flip the x and y's. So the x was with the b, well, now the y is with the b. B to the y equals x.
So b to the y equals x is the inverse of y.
It's the b to the y if x is not the inverse of log, but exponentials and logs are inverses of each other. So you know how like I don't know if you remember but at some point we found the inverse of x squared plus 3. Remember that? And what function did it give me?
Uh,
The square root, right?
yeah, that's where.
This is because not exponentials, but quadratics like squares and square roots are inverses of each other. Logs and exponentials are inverses of each other. But these two are not inverses of each other. They're equal to each other. They're the same thing, right? You don't really need to know that. I'm just kind of talking, but that's it. Yeah. Any questions here, guys? That's really important. How to switch between the two. That is important. You do need to know how to switch between the two. And that's how you do it. Base of the log is base of the exponent. Flip the x and y's. All right. So now we're gonna have some practice. We're gonna flip some of these into exponential form. All right. So log base 4 of 16 equals 2. Well, for 1, log base 4 of 16 equals 2. So remember, that's going to be the same thing. Take the base of the log, which is 4, and then flip these two. Base of the log is base of the exponent, and then you flip both of these. So 4 squared equals 16, which, we know is true. Then we have log 5 of 0.2 equals negative 1. Well, just like before, take the base of the log, make it the base of the exponent, then flip the two numbers. 5 to the 5 to the negative 1 equals 0.2. Sorry?
That's true.
It is true, yeah. 1/5. Yes. So log 8 of 1 equals 0. Well, just like before, base of the log is the base of the exponent. Then flip these two. 8 to the 0 is 1. And anything to the power 0 is 1. Everyone following me, guys? Are we okay? All right. And then 4. Log 23 of 1 equals 0. Well, base of the log becomes base of the exponent. Flip both of these. 23 to the 0 equals 1. Everyone with me, guys? Any questions? All right, let's keep going. Now write each equation in logarithmic form. So now we have exponents. We're going to put these into log form. And it's the same logic. So 5, we have 2 to the 4th equals 16. Well, now we're just going to do it backwards. The base of the exponent is now the base of the log. And then flip these two numbers. It's going to be the same logic all the time. Base of the exponent is base of the log. Flip the two numbers. (27 to the 1/3) equals 3. Base of the exponent becomes base of the log. So log of 27. And then flip these two. So log base 27 of 3 is 1/3. Everyone with me, guys? Any questions?
What's log?
That's a great question, man. It's just log is just log, man. Everyone thinks about it, but then they just kind of move on with their lives. Log is just log. Math is just math. So 1/4 and a -2 equals 16. Again, log of the exponent becomes log of the base. So log of 1/4. You flip these two. So log 1/4 of 16 equals -2. Everyone with me, guys? Ready to keep going? All right, let's keep going. Equivalence property of exponents. This is another one of those common sense things. It's basically just saying, look, if 2 to the 3rd equals 2 to the 3rd, then they're the same thing. Because it's saying if b to the x equals b to the y, then x equals y, right? That's all it's saying. It's essentially saying this. Ready to keep going, guys? All right. So now we're going to evaluate each expression. So now we're actually going to take what we learned and kind of try to solve it. I promise you this isn't really that bad. Yes. Come here. All right, so I want to know what is log base 12 of 144, right? Well, if I ever tell you to evaluate something, what I'll do is just set it equal to x. So log base 12 of 144, it equals some value x that I don't know. Okay? And then just put it into exponent form. Log form, in my opinion, is kind of, I don't want to say it's useless, but you can't really solve with it. Anytime you have logs, you're just going to put it into exponents to solve it. So now I want to know, well, 12 to the x equals 144. Well, what's x going to be? 2, right? 12 squared is 144. That's your answer. X is 2, so that means log base 12 of 144 is 2. So anytime I tell you evaluate a log, just set it equal to x, put it into an exponent, and solve from there. Make sense, guys? All right. 9 log base 64 of 8. We'll evaluate this. Same thing. Set it equal to x. And now you have 64 to the x equals 8. Everyone with me? So from here, well, the square root of 64 gives you 8, right? Y'all know the square root just means a power of 1/2, right? So 64 to the 1/2, that is the square root of 64. Have you learned that yet? Okay, so exponents to a power is just the root. And I think y'all learned in like the very first 2 weeks in the other class, I think. Because I remember helping someone with this stuff before. All right, well, now I'm teaching to you now. When you have a power, it's going to put it as an exponent. Or as a, if you have a power of a fraction, it puts it into a root. So 64 to the 1/2 is the square root of 64. If you have, we're going to do this in a bit, but 27 to the 1/3 is the cube root of 27. I'll say those are the two big ones to know. Anything to the power of 1/2 is a square root. Anything to the power of 1/3 is a cube root. Because, well, it's not important, but that's what it is. Yeah. The index. So it's cube root, so it's like this. So if 27 to the 1/3, anything to the power of 1/3 is always the cube root of that base. So 27 to the 1/3 is the cube root of 27. We okay with that? Yes. So 6x in this case equals 1/2. Ready to keep going? So 10, now we have log, was it base 3 of 127? So log base 3 of 1 over 27. That's what I'm going to figure out, well, what is it? So set this equal to x. Well, 3 to the x equals 1 over 27. I guess I'll show you a different way to do this. It might be a little easier. Well, not easier, but it's a different way to solve it. We have 3 to the x, right? Well, 1 over 27, isn't that the same thing as 27 to the negative 1? Are y'all fine with that? You can always flip something and put it to the power of negative 1. 1 over 27 is the same thing as 27 to the negative 1. I don't want to say I took away the fraction, I flipped the base. If you flip the base, you can raise it to a negative power. Are we fine with that? All right. Well, 27, isn't that the same thing as 3 to the 3rd? Right, 3 times 3 times 3 is 27, right? Everyone with me up to here? Well, did y'all at least learn that power to a power you multiply? So 3 to the 3rd to the negative 1, that's 3 to the negative 3. Did you learn that or no? Yes, no. You're supposed to. So 3 squared to the 3rd power is 3 to the 6. Anytime you have power to a power like this, you multiply them. So 2 times 3 is 6. So 3 to the 4th squared will be 3 to the 8th. This is kind of an aside. Power to a power, you're going to multiply them. Are we, everyone fine with me? Following? Yes, you have 3 to the third to negative 1, right? So 3 to negative 1 is, well, is 3 times negative 1 or negative 3. Sorry? This is more of an aside. I'm kind of just showing y'all how that rule works. That's it. Everyone up to here will be fine. So x is negative 3. And you could have solved the other ones this way as well, as the other ones were a little easy to kind of see the pattern. Um, but you could have solved them this way as well. You get the same thing. Everyone with me? Okay. Yeah, I guess here on the previous one, if you really wanted to, you could have said, oh well, 64 to the x, that's just 8 squared to the x. So 8 to the 2x equals 8 to the first power. Right, 64 is 8 squared, and 8 squared to the x is 2x. Are y'all fine with what I'm doing there or not really?
I mean, the way I saw it, it was like
You can do that. It works. Well, 64 is 8 squared, right? Right? 64 is 8 squared to the x, or 8 to the 2x equals 8, or 2x equals 1, right? Or x is 1/2. And that's the same thing. Confused? What part's confusing you? Okay, so 64. I'm starting from 64 to the x equals 8, right? Well, isn't 64 8 squared? So can't I take 64 and rewrite it as 8 squared? So 8 squared to the x, right? Equals 8. Well, 8, remember, power to a power you multiply. So 2 times x is 2x. So 8 to the 2x equals 8 to the 1. So 2x equals 1. So 2x equals 1 or x equals 1/2. Make sense? Everyone else, are we okay? Questions? This way? Yeah, to be honest, yes. Oh, it's not that 8 2x equal turn to 8 1, but I'm starting from this right here. So 64 to the x, right? Isn't 64 the same as 8 squared? So I can take 64 and rewrite it as 8 squared to the x. And 8 is just 8 to the first power. I'm just bringing this along. So 8 to the 8 squared to the x is just 8 to the 2x, and it's 8 to the 1 state 8 to the 1. Well, 2x has to equal 1, right? So 2x equals 1, you solve for x, x is 1/2. Make more sense? Essentially, yeah, because they're the same thing in the bottom. You can say, oh, well, they're the same thing. I don't care for this anymore. So 2x equals 1. Make sense now? Everyone else, are we okay? Any questions about anything? Before I keep going? All right. Definition of common and natural logs. So these aren't anything special. They're just very common logs. So we write them. They have special notation. They don't have any special rules. They just have special notation because they're really commonly used. We have the common log. That's base 10. Because base 10 is so commonly used, all we do is say, well, y equals log x. So anytime you don't see a base, that means it is base 10. And then we have log base e of x, and that's called the natural log. We don't write log base e, we just write ln of x. And again, that's because the natural log is kind of happens in nature a lot. It's also pretty commonly used. So they call it the natural log and it gets its own special notation. But again, no special rules, just special notation. Yes, E is like 2.17 something or 2.71, something like that. It's actually used pretty much every day. You just don't realize it. It's used a lot in interest and all that kind of stuff, natural growth, all that kind of stuff. So math is useful sometimes. Any questions here? Ready to keep going?
L.
ln of x, yes. So they're not putting parentheses. I like to just to make it nice, but that's essentially what it is. Cool. All right. So now we're gonna evaluate these. So 11 log of 100. So remember, anytime you want to evaluate a log, just set it equal to x. And because I don't have a base here, that tells me, well, it has to be 10. Yep. So I can rewrite this as 10 to the x equals 100. I mean, this pretty obviously is going to be 2, but let's do it the way we just learned. 10 to the x, 100 is 10 squared. So x is 2. Everyone with me? So 100 is 10 squared. So tens are pretty nice. How many zeros you have tells you what the power is going to be. So 100 is 10 squared. 1,000 is 10 cubed. 10,000 is 10 to the fourth. The amount of zeros you have tells you what the power is. Rather than 10 has 1 0, it's 10 to the first. Sorry? Yeah, one of the few numbers that works kind of nice. Sorry? Yeah, you say that, but it gets worse. Huh, don't jinx it. All right, so 12, we have log of 0.0001. Well, I don't have, well, we set it equal to x first. And that is 10. Okay, so 10 to the x equals 0.0001. So there is a rule when it comes to fractions, or decimals, sorry, to change them into fractions. A pretty nice rule, to be honest. Uh, Again, as an aside, if you have, let's say 1 over 10, 1 over 100, or let's go the other way, sorry, 0.01. 0.01. That's 1 over 100, right? Y'all see how 0.01 is 1 over 100? How it works is that whatever the number is, in this case 1, you put it on top, and the amount of decimal places you have tells you how many zeros are in the bottom. So if you have 0.25 or a quarter, that's 25 over, I have 2 decimal places, 100. 25 over 100 or 1/4, which is the exact same thing. Does that make sense what I'm saying? You can always change a decimal to a fraction, and this is kind of how you do it. Whatever the number is in the decimal, so like as an example, 0.25, put it 25 over however decimal places you have. In this case it's 2, 0.25 is 2, so it's 100. You have 2 zeros. So in this case, 0.001, I can rewrite this as 1 over 1 of 1, 2, 3, 4, 1, 2, 3, 4 zeros. Make sense? And then from here, well, 1 over 10,000 is 10 to the fourth, right? We have 4 zeros, so 10 to the fourth. And then you can flip this fraction to make it 10 to the negative 4. Right, you can always flip a fraction by raising it to a negative power. So 1 over 10 to the fourth is just 10 to the negative 4. Right, flip the fraction, raise it to a negative power. Everyone with me? Any questions before I keep going? That's good. Because stuff really, it's not bad. It's weird because you're starting to see like logs and stuff, and doesn't really have like a set thing to do it to work with. But it just takes practice. So in this case, x is negative 4. Make sense, guys? Any questions? All right, let's keep going. Or we have more problems, actually. We have one more. Ln to e to negative 3. Ln e to the negative 3. Well, again, just set this equal to x. So remember, natural log is just a base of e. So what you really have is e to the negative 3, sorry, e to the x equals e to the negative 3. So x equals negative 3. Make sense? Go ahead. Yeah, natural log ln is always base of e. Make sense? Everyone else, are we okay?
Is E to U?
E's, I'm sorry?
Is E to U?
Euler's number, yes. Always read 12 twice is 13. Yes, exactly. And now we have natural log e to the 10. So again, set it equal to x. This is technically base e. So we have e to the x equals e to the 10, or x equals 10. Are you ready to keep going, guys? Ready? Okay. Whoops. All right, so these are some basic properties of logs. So log base of 1 always equals 0. Log base b of b is always 1. Log base b of b to the x is always equal to x. These two are kind of the same thing. And b log b to the x equals x. And I mean, all three of these are kind of the same thing, to be honest. The first one you don't really need to have memorized because you can kind of just solve it. Well, I don't want to say that. You should know it, but yeah, I should just know it. Ready to keep going, guys? Yeah, I'm going to show you some examples of these in a second, unless the book's going to give it to me anyway. So just write these down. When you see some examples, it'll make more sense. When you just see letters and just letters, really gets really confusing. When the actual application's pretty easy. Are you all good? Sure.
Okay.
Good. All right. So they have some examples. They do. All right. Essentially, what all this stuff is saying is that the base of the log. So in this case, let's do 19. We have log base 19 of 19, right? Well, let's actually write it like this: 19 to the first power. If the base of the log and the number you're taking the log of are the same thing, these cancel out, and you're just left with 1. Make sense? We'll write this down. I'm going to show you what we did before. Maybe it'll kind of click a little bit better. Are you have this written down? So if you go back here, let's look at number 11. Well, we have log base 10 of 100, right? Isn't 110 squared? So we have log 10 of 10 squared, right? Well, these cancel out and you're left with 2. That was our answer. You didn't have to do all that now. And that's kind of how it works. If the base of the log and what you're taking the log of are the same, they cancel out and you're just left with the exponent. And it's because of all this. If you reworked it out, you have 10 to the x equals 100. 10 to the x is 10 squared, or just 2. It's kind of just shortening this whole process up. All right. So now 20. So 20 log base 10, or log of 10, which is base of 10. And remember, that's 10 to the first power. And the log is technically 10. It's just 1. The log base 10 and the 10 cancel out, and you're just left with 1. Everyone with me, guys? So 21 log base e. Well, log is base 10, right? These aren't the same. You can't really do anything here. Just leave it log base 10. I think they meant natural log, but I'm not changing that. Because the base of the log and what you're taking the log of are not the same, it's 10 and e. They're not the same thing. You can't do anything. Make sense? What's wrong? I mean, it does have a number, but you cannot solve this without a calculator, and we're not allowed to use calculator, so that's our answer. Yeah, 2.71 or 2.17. It's too late for me to think. I think it's that too, but yeah, 2.71. So 2.71828, etc. It's like pi. You know, pi is 3.14, and it keeps going on forever. E is the same thing, but it's 2.71. Okay. So because the base of log, the common log and ER aren't the same, you can't do anything. 22 log of 273 to the first power. Oops, 273 to the first power. Well, log base of anything of 1 is always going to be 0. Right? Because this is essentially asking 273 to what power equals 1. That's always going to be 0. So when you take the log of 1, it does not matter what the base is. It's always, it's always going to be 0. So it does not matter what the base of the log is. If you have log of something of 1, it will always be 0. So 273, 1007, 17, whatever. If if it is of 1, it's going to be equal to 0. We're fine here? Sorry? It was a rule, yes. So 23. Well, it was a rule, but also I think you actually see an example. It makes a little more sense. So now we have log of, I think it was 1/8. Yeah, 1/8 of 1. Same thing, what the base is doesn't matter. If you're taking a log of 1, it will be 0. Everyone with me? All right. Log 30 of 30 to the 10. Well, like we said before, the base of the log and what you're taking the log of are the same, 30 and 30. They're going to cancel out, and you're just left with 10. All right. Oop, 25. ln of e to the negative 12. So remember, ln is just a base of e. So these are going to cancel out, and you just have negative 12. Yes, ln of e to the negative 12.
So if you have L, it means that E is going to be there.
Yes, ln always means it's log base of e. Yep. 10 log of 14. So now it looks a little different. It's 10 raised to the log of 14, but it's the same rules. All you're doing is flipping the log and the e, or the log and the exponent, sorry. But it doesn't actually matter because it's 10 raised to the log of 10, right? Same thing. It doesn't matter how it is as long as they're kind of applying to each other. They cancel out, and you have 14. Make sense? You sure? Okay, that laugh was scaring me. All right. I'm sorry? Finally? Great. As long as it makes sense. 8 log 8 of 5. So 8 log base 8 of 5. And what's that going to be? Just 5. These are the same base. They cancel out. You just have 5. Yeah, it's reversed, but it kind of works both ways. So that's why it applies both ways. We're good here? Any questions? No? Sorry? I mean, you say that, but these are actually, sadly, they're very important. I mean, don't y'all think about all the stuff they kind of start saying, oh, there's exponential growth in this, or has exponential whatever. Like it comes from this stuff. Like the guy who invented Euler's number and all these numbers, like it came because they're trying to figure out interest actually. So the free money y'all get from banks and loans and stocks and all that kind of stuff. If it wasn't for this stuff, you wouldn't be making free money like that. If y'all are investing that kind of stuff. Sorry, trying to. It's hard to get into, man. Yeah. So let's go ahead. Let's see how complicated we're getting the graph to be. All right, we're not getting too complicated. Great. All right. So log base, we're gonna graph log base 3 of x. So honestly, the way I do these is what I like to do is I like to change this to an exponent. I don't like to graph as a log. I think it's confusing for me. I just change and say, oh, well, this is going to be 3 to the y equals x. I change it to an exponent, and then I plug in y's to solve for my x value. Does that kind of make sense what I'm saying? Y'all remember how we graphed exponential functions? We plugged in x values and solved for y. Well, now I'm just changing to an exponent because y is the power. I'm going to plug in y's to solve for x. So plug in 0. 3 to the 0, well, that's going to be 1. So x is 1 here. Plug in a y value of 1. Well, 3 to the 1 is 3. So x is 3. Does that make sense, guys? Yes, no, I can do it again. Do it again? Okay. So what I do, graphing as a log is kind of weird. They have these weird rules to do, and I think it's a lot of memorization. I don't like it. So what I do is I change this to an exponent, right? So the base of the log is the base of the exponent, and you switch x and y, right? So 3 to the y equals x. Make sense? And because now the x is by itself instead of the y, what I'm going to do is I'm going to plug in y values to solve for x. So when y is 0, right? Every time we did an exponential before, we plugged in x's, like a 0 for x, so that was the exponent. Well, now the y is the exponent. So you kind of do it opposite. So when y is 0, you have 3 to the 0, which is 1, right? So x is 1 because x equals 3 to the y. And then when y is 1, you have 3 to the 1. Well, that's 3. So that's 3. Make sense, guys? So that's how you graph it. And also, there is an asymptote here, right? Logs will have an asymptote too, but it's the opposite asymptote. These always kind of work backwards. So in this case, the asymptote is always with the x. So in this case, we have y equals log 3 of x, right? Isn't that technically x minus 0, which is just x? So it's y equals 0 is the asymptote here. X equals 0, sorry, x equals 0. That's the asymptote. The asymptote for logs are inside, while the asymptote for exponents are outside. Does that kind of make sense or not really? If not, you could always look at the exponential function. Is this the same thing as 3 to the y plus 0 equals x? So same thing, this is still your asymptote of 0, but it's going to be x instead of y. And then plug in the points. You have 1, 0 and 3, 1. And it's going to look like this. Yes, vertical asymptote. Did I say horizontal? Yeah, so before is horizontal. With logs is vertical. So remember they're inverses of each other, so everything kind of flips. So an exponential, a logarithmic function is kind of a horizontal function, kind of flipped over. Yes. Logs always have vertical asymptotes, exponentials have horizontal. Everyone with me? All right. So this one, we're not graphing it. They graphed it for us. All we're going to do is just figure out its domain, range, and its asymptote. So in this case, my asymptote is pretty easy to find. It's in there, so it's x equals -3. That's my asymptote. So I should write it over here. Vertical asymptote. That's x equals -3. Make sense, guys? All right. Your domain is always going to be from your vertical asymptote outwards, so from -3 to infinity. And you can kind of look at the graph. You start at -3 and go to the right forever. That's the domain. And the range is all real numbers. Everyone with me, guys? Any questions? For logs, yes. Ready to keep going, guys? No? Take your time, guys. This stuff isn't easy.
So domain would start with the
Asymptote. Yes. All right. Last problem of the day is the same thing as before. This domain, range, and asymptote. Well, the asymptote, you see how it's just x by itself, so it's x equals 0. So vertical asymptote, that's going to be x equals 0. The domain is from 0 to infinity. And the range is all real numbers.
So what does the -2
It just flips it, so it makes it go down instead of up. You see how this one's starting from up and going down? And this starts down going up? It's kind of like growth and decay functions, essentially. Any questions here, guys? Go ahead. For logs, yes. It'll always be all reals. Sorry?
the positive?
No, it's always least to greatest. So negative infinity to positive infinity. Everyone with me, guys? Any questions? I think that's the last question of the day. A lot to go through, but we're actually able to finish it relatively early. All right. That's all I have. You can come get your test if you want. Let me stop recording and take attendance. Y'all can